Good afternoon, dear ladies and gentlemen. On behalf of the Baltic-German University Liaison Office, I would like to welcome you to seminar Baltic Sea Environment, Challenges and Opportunities. And first of all, I would like to introduce you briefly to the Baltic-German University Liaison Office. Its main aim is to act as a scientific bridge between the Baltic states and Germany by providing a platform for scientists to discuss current topics, by supporting scientific projects and organizing scientific events like this seminar today. And the Baltic Sea is a unique and fragile ecosystem. Overfishing, pollution, and climate change have severely affected its environment, but there are measures to counteract this development. And for this reason, we have invited two competent speakers from Germany and from Estonia to discuss the challenges and opportunities regarding the Baltic Sea region. And we will start with the presentation, Chemical Pollutants in the Baltic Sea, Trends and Risks, by Professor Detlef Schulz-Bull. And afterwards, the presentation, Environmental Status of Estonian Marine Areas and Possibilities for Improvement, by Professor Urmas. And after the lecture and the presentation, you will have an opportunity to ask questions or to add your comments. And however, before we begin, I would like you to meet our first speaker, Professor Detlef Schulz-Bull. And he's a marine chemist and the director of the Leibniz Institute for Baltic Sea Research, Warnemünde. He's also a professor at the University of Rostock. His research focuses on the development of sampling techniques and analytical methods for the determination of organic trace substances in the marine environment. Yes, and I would like to ask you, please sign everybody on the list that is going around. And now, thank you very much for finding time to come this long way here to Tallinn. And now the floor is yours, please.
Okay, thank you for the nice invitation to come to Tallinn, and thank you for joining. As you heard, and thank you for the nice introduction, as you heard, I'm a marine chemist, and I'm wondering if there are any marine chemists around. Yeah, great, at least one. Okay, and oceanographers, so a few ones. Okay, so I decided to give you first a very brief introduction into the Baltic Sea and why the Baltic Sea has these big environmental pollution problems. And this is related to the water cycle, to the catchment, to pollution hotspots. Then in the second part, I will give you some information and some examples from organic contaminants, different types of contaminants, and I end up with a summary and an outlook. So this is the Baltic Sea. We are over there in Tallinn. It's not active, you see. And I came from Rostock, from the southwestern part of the Baltic. And the Baltic is a typical, from an oceanographic view, a typical estuary, a big estuary system. But it's unusual because we have the shallow parts in the southwest and some deeper parts in the middle of the Baltic. The Gotland Deep, the Landsort Deep, the Bornholm Deep. This is not typical for a system like this. And the volume of the Baltic is 630,000 cubic kilometer. The area of the Baltic is very large. It's bigger than the area of Germany. And we have distances of about 1,000 kilometers from north to south and west to east. And the Baltic Sea is relatively shallow. The mean depth is only about 50 meters. And the maximum depth is 460 meters about. Do you know where this is? The deepest part of the Baltic Sea? It's the Landsort Deep near Stockholm. And it's a very narrow, deep hole in the Baltic Sea. The water one. Yeah. So the water budget of the Baltic Sea is given in this slide. So overall, we have an input of water from the atmosphere, precipitation, from the rivers, from land, and we have some input from the North Sea, the inflow water. We have a connection to the North Atlantic in this Skagerrak area. And then we have shallow parts and shallow zilts that prevents the Baltic from a normal estuarine circulation. So the outflow water, about 950 square kilometer, is bigger than the inflow from the North Atlantic. And it's balanced by higher precipitation and higher river water inflow than precipitation, than evaporation into the atmosphere. So in general, the budget is closed. And the result of this is that we have two layers in the Baltic Sea, at least two layers, the surface zone and the deep zone in the central Baltic. And these two areas are connected by halocline, that means changes of salinity, or thermocline, changes in temperature. And the halocline is more important for the Baltic Sea because the deeper water in the central Baltic has higher density than the upper layer surface water. So there's no mixing between these two water types. That means the central parts of the Baltic, the deep parts of the Baltics are closed from exchange with the North Atlantic. The second very important thing is that we have a large catchment area. In light green, you can see the catchment area of the Baltic Sea, and it's 3 times the size of the Baltic Sea water. And the catchment area includes almost all countries around the Baltic Sea: Sweden, Finland, the Baltic states, Russia, Poland, Germany, and Denmark. And all water that comes from the rivers of these land is entering into the Baltic Sea. That means all chemicals that we put into our water cycle on land ends up in the Baltic Sea. And the HELCOM, the Helsinki Commission, recognized these big problems decades ago. And they identified so-called hotspot areas. So where do pollutants, where do chemicals enter into the Baltic Sea? And they identified hundreds of these places: wastewater treatments, industrial areas, other sources. All these hotspots are identified and they are recognized as a thing as places where we have to do action, where we have to clean the water that enters the Baltic Sea. And we are still on the way to do this. And as you can see here, these hotspots are not only near the coast, but they are also inland, far away from the Baltic Sea itself. So what are the consequences of these special features of the Baltic Sea? First, the Baltic Sea has a low water exchange with the North Atlantic, much lower than it is in the North Sea, for instance, with the North Atlantic. The residence time is more than 30 years, and the residence time of the water in the deeper parts of the Baltic Sea is even longer. That means the Baltic Sea is a trap for substances that enters into the Baltic Sea and keep them for years, for decades, for centuries. And the things are the deep water in the deep part of the Baltic and the sediments, especially the organic rich sediments. And there are strong regional differences of pollutant input according to the hotspots, to the different sources. Coming to the problem why the Baltic Sea is so high polluted with chemicals, known for many, many years. First, we are the reason for that. The population is 85 million people living around the Baltic, living in the catchment area of the Baltic Sea. There is get this. bit. Okay. There is a lot of industry in the area of the Baltic Sea, not in all regions, but more in Poland and in the southern regions, we have a lot of industry. It didn't react anymore. So a lot of agriculture is taking place in the catchment areas. And we have many offshore activities like shipping or drilling or building pipelines or building wind parks at the moment. So what is the problem with the contaminants now? So we have a production of these chemicals on land. And these chemicals enter the Baltic Sea via the atmosphere, that is the emission, or via riverine input or direct input. And then we have a difficult pathway how these chemicals went into the Baltic Sea and behave in the environment. First, we have dry and wet deposition, air-sea exchange processes. That means all substances enter in the upper layer, in the surface layer. And as I told you before, this layer is closed, has no connection to the deeper parts of the Baltic. But we have a transport of water and contaminants from the surface to the deep by particle formation, by particles. And all organic material that is growing, algae that are growing in the surface, take up these organics and these pollutants and transport them into the deep. In the deeper water, we have desorption, adsorption processes, we have degradation, and at the end, the material ends in the sediment. So the sediment and the deep water of the Baltic Sea is one of the, are the main sinks for these components. In the meantime, we have many processes going on with marine biota, like bioaccumulation, bioconcentration, degradation. Many compounds are metabolized and form new substances, very, very difficult reactions and processes. At the end, with the fish, these contaminants come back to us again. The first example, or examples I will present you are from the POP, the so-called persistent organic pollutants. This is an old story. The Stockholm Convention almost 20, 30 years ago identified many, many compounds that are toxic, persistent in the environment, and concentrate in marine organisms. These so-called POPs were mainly chlorinated and aromatic chemical substances. I give you some examples here that are the PCBs, polychlorinated biphenyls, the well-known dioxins, TCDD, tetrachlorodibenzodioxin, aromatic hydrocarbons, and hexachlorocyclohexane, the so-called or the well-known lindan, and many, many others. Do you know more? Chlorinated and aromatic chemical substances that are toxic. One famous compound is a DDT, a pesticide, insecticide. Okay, these compounds concentrate in the marine food web. So we have very, very low concentrations in water, higher concentrations in sediment. The concentrations in water are really low. They are in the picogram per liter range, almost nothing. 10 minus 12 grams per liter seems to be not important, but it is. Then these compounds are stable and they accumulate in a food chain. That means they concentrate if you go up. If you come from water to diatoms, diatoms is really 100,000 times higher. And then diatom is an algae. And then zooplankton and fish up to herring, they concentrate these hops during their feeding and their life. And on the upper part, you can see a harbor porpoise that has really extreme high concentrations of these compounds in the body and the blubber. And this all starts with low concentration in the water. So we have to prevent the water from these compounds. Do you know where we are in this line? We have all PCBs in our body, unfortunately. So we are a little bit in between the herring and the harbor porpoise, because we don't eat only fish, we eat also other things that are not so exposed. And do you know what humans have the highest concentration in their body? That are the Inuits, that was studied decades ago. So the Inuits in Greenland, they eat whales and blubber. So they even higher than these harbor porpoise, heavily polluted, far away from the source of these compounds. We took a lot of action after we know all about this. And HELCOM did a lot of action. And the Stockholm Convention, they didn't allow the production and the usage of these compounds anymore. And do we see a positive trend? Yes, of course, we see a positive trend in sediments. What we do, we go out at sea, we took samples with a so-called multicorer. We got these cores, and you can see that there are lines in this core. They are laminated. That means they are not disturbed, and we can reconstruct the cores in time. And if we do that, we can identify, for instance, here, this is for the aromatic hydrocarbons, and we can date these cores. And if we date them by mercury, we can use a mercury values, or we can identify them by the cesium-137. Do you know where this cesium came from? That is a Chernobyl peak. And we know exactly when we go into the sediment and we find the cesium maximum, we know this is 1987. This was a Chernobyl fallout. And so this is an excellent marker for us now to go down in the core and identify when the sedimentation took place. And with that, we can identify the maximum of the concentration in sediments. That means the maximum of the input. And for many people, for many compounds, like the aromatic hydrocarbons, also PCBs and DDTs and dioxin, the maximum was about 1970. And since that, we can show a positive trend, a decreasing trend of these compounds in sediments. Another POP, persistent organic pollutant, is the lindan, the HCH, the hexachlorocyclohexane. And this was, the production was banned, and it was not allowed to use these insecticide anymore. And so we have, this is, here we start with 1970, and this is today. And within these 70 years, we have measurements almost every year. And you can see a strong, good trend in these compounds. It took 50 years to reduce the concentration like this in the Baltic Sea. And this is why these cyclohexanes are relatively water soluble, so they do not go into the deeper parts, they do not go into the sediments, they stay in the surface. And with the residence time of the surface water and the half-life of about 30 years, you can see this good trend in these compounds. But we have to wait very, very long to see a trend like this. We don't see a trend like this for PCBs in the last 20 years or for aromatic hydrocarbons. The aromatic hydrocarbons came from shipping, from activities. You see almost no good positive trend at all. And for PCBs, you see a very, very slow trend. And I calculated that it will need 100 years to get the surface water of the Baltic Sea clean with PCBs. That means below the detection limit. So the residence time is still the problem. So summary for these group of contaminants, PCBs, DDTs, dioxins, and so on. The production and use is prohibited. This is a good information. Only small input from land sources since the year 2000 can identify. Still, we have in the catchment area reservoirs of these compounds that may influence and enter into the Baltic Sea. We see decreasing trends in seawater and in sediments. In sediments, we can identify the maximum of concentration is about 1970, but we have long residence time in the marine environment. And the half-life of these compounds is more than 100 years. But for us, or for the politics, no further action is useful. We monitor these compounds, but we can't see any big problem upcoming in the future. Go to another group, a new group, contaminants of emerging concern, CEC named. What are these? This is now under debate or under a big debate and discussion in HELCOM green expert groups. We focused on pharmaceuticals like the diclofenac, on the UV filters like octocrylane, on hormones like estradiol, and on new pesticides like glyphosate. And I can bring up more than 200, 300 of chemicals that we do not know very much about in the Baltic Sea. And these contaminants of emerging concern are the upcoming work for the marine chemists and analytical chemists in the environment of the Baltic Sea. We started with some PhDs on that. For instance, we had a study near Rostock and along the coast of the UV filters. And one of the two major UV filters are PBSA and octocrylane. And Katrin Fisch, one of my PhD, she analyzed she established a method to analyze these compounds in seawater. Then she did some basic measurements along the coast and along the river, Warnow, up to a wastewater treatment. And the highest concentration she found are here in the wastewater treatment area. So this is a clear sign that these compounds came from Rostock, from the citizens. And along the coast, she found seasonality. For instance, in summertime, when the tourists are coming and they go out for swimming, she found really high concentration of these UV filters from sun creams in the Baltic Sea, higher than the threshold values. So this is really a direct input by humans along the beach during summer season is clearly identified. And pharmaceuticals, antibiotica, or salicylic acid, anti-inflammatory, main compounds of these new pharmaceuticals entering the Baltic Sea. The same study and the same station, and this was almost everywhere found in high concentration. So these compounds are really persistent, stable, they stay in the environment, and they are the upcoming problem for the Baltic Sea research and environmental ecotoxicology. Summary, contaminants of emerging concern. We have increasing concentration in the environment, totally different from the persistent organic pollutants from the POPs. Only little is known about the environmental behavior. We do not know how toxic these compounds are. In marine animals is nothing known, nothing measured. The most CSCs are not very persistent, so they are degraded in the environment, but the metabolites are not studied. So we do not know what problem behind is there upcoming. That means more research is urgently needed to do studies and environmental measurements of contaminants of emerging concern. Nutrients. Many of you know about the nutrients, and this is the phosphate concentration in the winter, the mixed layer in the Gotland Basin. It's a wrong slide, sorry, it's in German. But you see in the 1960s, when we started these measurements in Warnemünde, in the monitoring, this is the natural background, nearly the natural background concentration. So phosphate is not a contaminant, it's also a nutrient. It's needed for the environment. And the critical thing is the high phosphate concentrations we found. And we did not understand the whole system of the phosphate, the cycling of these compounds. But what we can see is a strong increase in the 60s and 70s. Then the phosphate concentration seems to be stable in time. And all the effort we did in the catchment areas to get the phosphate out of the water, of the wastewater and of the river water, has not a big effect in the Baltic Sea at the moment. And this again is related to the very, very high residence time. The Baltic Sea is a trap also for phosphate. And the deep Baltic and the sediments keep the phosphate and are also possible sources for phosphate in the future. So the problem is even bigger than it seems. Background concentration, increasing concentration due to the phosphate was used for washing, detergentia, and so on, and in the agriculture. And then we stabilized the input of phosphate, or we also decreased the input of phosphate from land, but this doesn't have a big effect at the moment. It needs more time. So the eutrophication of the Baltic Sea is still under debate, and it's one of the major things of the holistic assessments of the Baltic Sea done by HERCOM every 5 years or so, every 3 to 5 years, almost,
5, 6 now.
5 to 6. It's always a delay in that. And yeah, we studied and we know where the phosphate and nitrate and other nutrients enters into the Baltic Sea. And we try to get, or the people try to get ideas how to reduce these input of nutrients. But also if you do, and if you be effective in that, it will need time to get the Baltic Sea back into the status. This is silicate, and oxygen has an effect on the input of nutrients at all. Everybody knows about the oxygen problem in the central Baltic Sea, the anoxic zones, and this is all related to nutrient cycles. So finally, there is much to do for all of us to understand the system, to save the Baltic Sea. We have to study the new contaminants, a big number. We have much more things to look at. For instance, the nanoplastic in the Baltic Sea. We have munition and chemical weapons in the Baltic Sea, in the sediments. And we have pollution by shipping, by offshore activities, or by pipelines. So this keeps us busy, and I hope one of you will join us and will help us to get the Baltic Sea cleaner and to save the Baltic Sea. Thank you.
Thank you very much for your very descriptive and interesting lecture. Now you have time for questions or comments.
Yes.
Thank you for the talk. I was thinking now, you were saying that there is not much knowledge about the effect of these emerging contaminants on the marine life. Are you establishing or planning to establish any collaboration with biologists, with the ecologists, to put both together knowledge you from the chemical side and then from the ecological side to see which are the potential effects of these contaminants and how this can eventually propagate into massive or more important ecological effects?
Yeah, of course. This is ongoing work, of course, yes. And the big story behind is you can take a single compound and measure it, the effect on an organism in a lab study or so. But this is not the thing you have. What you have in the environment are many, many of these compounds together. And you have the metabolites, and you have very, very changing concentrations, and you have to establish these, the real world. And this is a complicated thing. And we actually we use eDNR also to get an idea, and yes, and computer software to identify these close connections of these synergetic effects in the real environment. It's a very, very difficult thing. Ongoing work on that is done.
Yeah, thank you very much for the presentation. And I just wondering, there are one more group of contaminants, also this POPs or persistent organic pollutants. So this is a polybrominated diphenyl ethers. So we have seems quite large problems with them, because they are exceeding thresholds everywhere and in every environment.
Yeah,
information.
This is right. This is a group very similar to the PCBs and the dioxins, and it put it in the same range. They are also part of these POP group, There are 12 compounds. I only show examples for 4 of them. And also another very important group is the PFAS. This is also upcoming debate now. And yes, this is the new contaminants, and the numbers are almost increasing.
If there are so many new contaminants coming, how can possibly monitor all of them?
We cannot, definitely. So the EU Water Framework Directive, this is one regulatory group looking at that, and you can avoid, the only thing you can really do is to avoid that these compounds enters into the water cycle. And this is, we start here with us in our toilet or in our washing rooms, that we don't throw medicine in that. This is the only thing really we can be active in. We know what is in the river water. We know what is in the wastewater from wastewater treatments. We know what is in the river water, and then we have an idea where, in what group we should look into the Baltic Sea. And then if we know about the half-life of these compounds, the capacity to be degraded, then we have an idea where the hotspots or the compounds of interest are, or what are these compounds. And then we look specific. We can't look for everything what is there. It's not possible. And it's far away from monitoring. This first is the detection.
I have a further question. So if there are these new pesticides coming, could it be also part of like developing these pesticides that they have to check the life cycle? So after they use it for spraying the crops or something, then they also should provide at least some kind of information. How fast can it go to the river system or something like this?
Yeah.
Could it be one way how to tackle this?
This is another way, yes, and this is a way that they do this almost, and there's a reach. This is the regulation behind. And when you produce a compound nowadays, you have to do these measurements. What is the behavior? How reactive are they? What is the partitioning between water and particles and so on? But sometimes it failed. For instance, for glyphosate, it was the common knowledge that glyphosate doesn't enter into the water because it stays in the soil, but it didn't. So parts of it, a few percent, goes into the water phase. And this is enough to get high concentrations in river water and also in some part of the Baltic Sea. So it always needs 10 or 20 years from the first measurement to get a regulation. This is the pity for us as a scientist. We have to wait before we see the result of our research.
There is also one question in Zoom. Why there was a white color for P and eutrophication in some locations near the east coast of the sea? What does it mean? No measurements? Why?
No data. That means no data. All the data are not in a way that we believe it. So the database for all of these components are evaluated, and there are a lot of problems in measurements and in interpretation of the data. So the coverage is not 100%. We work on that.
Okay. If there are any more questions in Zoom, please raise your hand and you can ask also your question. And now if somebody else has questions here or comments.
I might ask one more question about this good old metals that we have. We have, I think, still the problem with pollution by metals. in the Baltic Sea. So what are the most severe metal pollution events in the Baltic at the moment? Are you aware of?
Yeah, so the most important metals are mercury and lead from a toxicity view. And this is
Cadmium,
cadmium, yes, copper also, and so on. But I would say overall the metals are well studied, and the pollution by metals is almost on a good way. So it's regulated and it's known. If we have new activities, for instance, for all these offshore buildings, then it may come into focus more in the future. Okay. Well, that's not the moment. So then, thanks again to everybody.
Thank you. I would like to thank you, Professor, for your nice lecture.
Thank you.
Thank you very much.
Thank you.
Let us continue our seminar with the presentation environmental status of Estonian marine areas and possibilities for improvement by Professor Urmas. He is an oceanographer, focusing his research on physical oceanography of the Baltic Sea, autonomous systems for continuous measurement of the marine environment, and assessments of the status of coastal and marine protected areas. In addition, he works as a professor at Tallinn University of Technology. Thank you very much for joining us today, and the floor is yours now, please.
Thank you. Okay, thank you, and thank you, Detlef, for this presentation. I can skip my introduction about the Baltic Sea, and I also will not concentrate on chemicals anymore. But I hope it will work here, like this. Yes, I will talk mostly about the Estonian marine areas and what we do and why we do so. Here you can see the Estonian marine areas, and we divide it into the coastal sea, into the territorial waters, and then the economic zone. And the frameworks that or why we do, or what are the programs we monitor and assess them. Of course, the first is the Estonian monitoring and assessment program for the whole environment, including also marine environment. Then we have EU Water Framework Directive, which assesses the surface waters and the groundwaters, but also the coastal sea for the ecological status, and including territorial sea for the chemical status. And the main instrument is nowadays the EU Marine Strategy Framework Directive, actually, which assesses the whole Estonian marine area, monitors and also assess what is the status and what we should do. And the main aim, or the initial aim for this Marine Strategy Framework Directive, was that we should reach this good environmental status by 2020. Now we are in 2023, it means that it passed. But we are still talking about it. It means that the politicians, they had a very good plan to fix it very quickly, but it didn't work. But there are other things there, or other frameworks where we work, for example, Health Comment, Baltic Sea Action Plan, Habitat Directive, Fisheries Commission, and so on and so on. It means that there are many activities that the environmental authorities do, and also the scientists do, to assess what is the status. And for the Marine Strategy Framework Directive, we assess the status using these so-called good environmental status descriptors, and they are divided by biodiversity, non-indigenous species, fishery, food web certification, seabed integrity, hydrographic changes, hazardous substances in food, marine litter, and underwater noise. And when we assess this, the assessment itself is not the final target. The final target is to improve the status, and it means that we have then to implement some measures to improve it or avoid the deterioration. Oops, something is happening. They can't see.
Yes, they couldn't see us. Hopefully now.
Okay, we hope so. And how it means that every 6th year we do the assessment, and then we suggest what have to be the measures to improve the status. And this time we actually worked for that from 2020 to 2022. And now we have this new program of measures in all countries, including Estonia. And the analysis was done almost according to these descriptors, but not exactly. Means that some ecological ecosystem components assessed separately, like birds, mammals, fish, pelagic habitats, and so on. But in principle, these were the topics that or components where we assessed it. And again, if you touch it, then it doesn't work. Okay, now it works. And how we did this analysis? The analysis is called analysis of sufficiency of measures. First we know the status, and we know the existing measures that what already are there. There are, because this environmental protection is we not started it yesterday. It was started many decades ago. We know that there are already measures. But we also know that human activities, they will develop. It means that there will be, we have to predict that what will happen in next 6-10 years. And then we have to calculate what will be the pressures to the sea, what will be the pressures in marine environment, knowing the existing measures and the projected pressures, we can assess that if we continue like this, only taking these measures that we have now, that it is called like business as usual, that we continue like this, then what will be the status then? And then we have different indicators which we have defined, that if the level of that indicator is at that place, then we can call that this component of the environment is now in good environmental status. And if we do this exercise, business as usual, and we know the target where we have to get, and we see that there is a gap. If there is a gap between the projected status and the good environmental status, we have to introduce new measures. And this was done according to those topics that I just showed you. And what kind of human activities we considered? Detlef already said that mostly it's from the land or human activities that we are there. There are physical restructuring of water bodies, for example, including also dredging and dumping, which is in the sea area. Then extraction of non-living resources like sand or gravel. Then production of energy. And again, if you talk about Estonia, then we don't have any offshore wind parks yet. And does that mean that we can skip them in the program of measures? No, we know that there are plans that there will be during that 6 or 10 years. It means that we have to think that what will be then the pressure, what will be the impact, and we have to have those measures in place that if they will be developed, then the status will not change to bad status if it's good now. Then extraction of living resources, of course, this is mostly fisheries. Then cultivation of living resources, either on land with the fresh water, but also in the sea. You know also that in Estonia, we don't have almost marine aquaculture. But there are so big plans. If Estonia produces now only 1,000 tons of fish in fish farms, then the plan is to have it 100,000 tons in the future. It means that someone has to calculate that what does that mean for the sea environment. Then transportation, then urban and industrial uses, which is mostly this wastewater treatment and disposal, then tourism, which is also quite important, and other things. These are the human activities that we analyzed, and what are the pressures that they produce on biological components. It's non-indigenous species, then activation of animal or plant species or aquaculture, then disturbance of species, for example, that we are running there at sea, and what does that what will be the impact, and then, of course, the fisheries. Then physical disturbance or loss. It means if we do something, for example, again, dredging and doing some developing some infrastructures, then during the work time we just disturb, but if we put there in the sea something, then it's a physical loss. But also if we have some dams and so on, then that we will change the hydrographic conditions. And then, of course, all these substances, nutrients, hazardous substances, litter, and also underwater noise. This was the program of measures in 2016, which again, it means that we already have measures. We have to take those into account in the analysis. And then we analyzed that what is the status and what will happen and what are the main problems. And it's not nothing new. We all know that the main thing is for the Baltic Sea is eutrophication, then hazardous substances, overfishing, non-indigenous species. Of course, non-indigenous species, they have not yet produced anything very dramatic in the Baltic, but in other areas it's the case. Then construction of infrastructure, marine litter, and noise. And to show you that what is happening, for example, in regarding the eutrophication or nutrients load, then this is the load of nitrogen from through the Estonian rivers. You see that for some time the load was growing, but now it's stabilized. But we still need to that it should be reduced. But for the phosphorus, you see that it's the trend is in the right direction. It means that, as Detlef showed you, that even if we have decreased the load, it's still in the sea. We can't see that, but the first thing we have to do is to decrease the trend. And in all areas of Baltic Sea, you see that the trend is that the load is decreasing, and hopefully taking into account the residence time at some place, we will have the good status, but not, of course, 2020 as it was the plan. And this is the Estonian waters, what is the status, and if it is green, it's very good or good, but you can't see it. It's the eutrophication status, it's all red. And if you take just nutrient levels, then in some places you can say that the levels are already okay, but and the direct effects, but if you do this integrated assessment, it's not full yet. And I will not talk about the hazardous substances, but the main thing I would like to show is here is that according to the latest assessment that we will produce a new one this year, the main problematic substances have been mercury, cadmium, lead, of course the cesium, but cesium it is going down now, and also TBT. It means these are the main, what are the, in Estonian coastal areas, you see this Gulf of Riga, Northern Baltic proper, and Gulf of Finland, and mostly these are the problematic things here. But of course, there are others as well. As one of these PVDs are also one of the problematic things. And it means that we know them for a long time already, but somehow they are still there, and we have to think that they are coming from. And this analysis, I will not show it or read it to you, but it's regarding all these topics like biodiversity, non-indigenous species, fish that what we discovered, that what kind of measures we have to implement on what components or in what pressures or human activities to improve the status of the Baltic Sea. And this is to the eutrophication as well. And these are the measures. That this is the main result of the analysis, and this program of measures has been approved in the beginning of this year. And here you can just read that what are the, for the biodiversity, the main thing is that since the biodiversity, it's in principle improving the status, but we say that all these pressures are influencing it. That means that to improve the status of biodiversity, we have to improve all hazardous substances, eutrophication, and so on. But for the itself, for the biodiversity, the main measure will be to improve the effectiveness of the existing network of marine protected areas. Do you know how many percent of the sea area is protected now, or what is the plan for the future in the Baltic? How much?
Around 20.
Yeah, it's about 20, but the plan is to have 30. But of course, I'm not sure if we just designate the areas, but is that enough, or we have to actually understand that how they are connected and to whom we do that? Are they seals, or are they birds, or are they other components? This is interesting. Then about the fish, we have 3 different measures. Then about the seabed, in principle, it's said that the benthic habitats are in good status, and it means that we do not need measures. But as I said, we will have all these wind parks and all those developments and aquaculture. It means that we have to design some measures that if they will develop that we have some guidelines how to do the environmental impact assessment, that what are the options that they can use to do some compensatory measures. For example, if they put the nutrients in, then they have to take also some nutrients out. Then about the eutrophication. Eutrophication is mostly managed at land. It is a marine program of measures. Then we have only one here, but I will show what we will do on land. But there's one nice measure is about the hydrography. We have been talking about that we have this dam between the Saaremaa Island and Muhu Island, and it stops the water exchange and also the migration of fish. But now it's decided that we will do the openings and open the strait again, and it will improve the status of that area. Then about hazardous substances, this is the pharmaceutical problem here. And the main thing actually is here that we can study the pharmaceuticals in the sea environment, that to protect it, the first thing is what we do. It means that this is mostly about how we have to raise awareness and do more environmentally friendly disposal of those. Otherwise, we can't manage it. Then also very nice measure is here that the government has agreed that we will build a new vessel, which is also for oil and other hazardous substances mitigation if something is happening at sea. But it also will have a capacity as a research vessel. That we have now one research vessel which is quite old, but in this case we will get a research vessel which is actually for all. And there are other, for example, the hazardous substances in aquaculture. They are again mostly pharmaceuticals, so but those used for in the fish farms. That these are not spread into the environment. There are 4 measures about the litter, and there is one about the underwater noise. And there are, of course, other so-called horizontal measures that we have to implement. And for the eutrophication, as I said, the main target is on land. And what are the main measures? It is introduced via this Water Framework Directive based water basin management plans, and mostly they are in agriculture, then sewage treatment, including in those areas, scattered dwellings, for example, then stormwater management. But also this is one which is from our program of measures, that there's local projects like in the Tallinn Bay and in the Haapsalu Bay. But one thing for the eutrophication is you see that we have now quantified that what is the impact of that measure, that we have to actually do this work as well as a scientists or experts, that what will all these measures will give into the nutrient load reduction, and is it enough or not? But since we don't know everything yet, the program of measures also includes scientific research topics, and this is something that who is now, for example, interested in DNA methodology, then you can go to the document and see what are the new topics that the government has agreed to finance in the coming years, and you can have those projects, for example, applications submitted to the Environmental Investment Center or Investment Center, that if there are calls, that these topics will be what will be financed. And when we did this program of measures, of course, then the authorities asked us that whether this is enough. And I just give you one example about the eutrophication or this nutrient input. And the BAP means the Baltic proper, Gulf of Finland, Gulf of Riga, and the colors here show that at the moment it's nitrogen load. The Estonia's case is so that we fail. The input is much larger than agreed nutrient inputs sailing, and then this is the estimate whether we can achieve the target during until 2030 or not. And the only place, I guess, it's the Gulf of Finland, not for the Baltic proper and not for the Gulf of Riga. It means that this 6 years, although we will implement all those measures, and why we can't do more? Because of economics. Sometimes it's not possible. And I am not talking about the status, I am talking about the input. Status, it will still take more and more time. This is about the nitrogen, and this is about the phosphorus. And in some cases, we know that the target is unrealistic for that area, but in principle, you see that it's still, we have measures, but it's still red. And this is for the Marine Strategy Framework Directive, that if we explain that why it's so that we can't achieve the good environmental status, then we have to explain those exceptions. And we have actually 3 exceptions. One is about the ringed seal abundance. It can't be achieved if we don't have ice. They just can't have higher abundances as now. And it's difficult to do something locally for that. In the case of eutrophication, again, it takes more time in the marine environment, but still also I would say that implement all these measures, it takes more time than we initially thought. And also about the hazardous substances, that there are some hazardous substances that we are not aware why mercury is still there. Or why cadmium? Of course, lead is very toxic, but we see the decrease in lead. But for example, in some places cadmium, in some places mercury, it's still there, and we need to understand that. But it's clear that we say that it's not possible, and it means that in some places and sometimes we will have some exceptional events where we are not happy about the status. And the last one is about the climate change. In these calculations, we didn't account for the climate change yet, but the eutrophication, it depends also about the temperature, stratification, and many things. That it means that, as Detlef also said, there is much to do yet, and those who are willing to study it, put their heads into that, then please, you are welcome.
Thank you very much for your very descriptive presentation. Now everybody has possibility to ask questions. Also, you in Zoom, you are welcome to raise your hand. Yes, please.
Yes, it's too much.
Too much. So maybe if there are no questions in the moment.
I have a question.
Yes,
You
please.
said that you're gonna have soon a new research boat, and the same boat is with hazardous oil.
Yes,
How big of the boat it is?
it's not, it's 40 meters.
Okay.
But both the options there are that you, for example, this, how to say, mitigation of oil accidents or hazardous substance accidents. It's not that it's built in. They will come with the containers. And if you have scientific work, you will come with the scientific container. If you have some other work, you will come with this equipment that is needed for that. But it's not a vessel which is for very quick reaction. It's mostly if there is an accident, then this vessel should be in 24, 36 hours place. Yes, there are plans how it works. We don't need the entire research vessel for the whole year. We don't have so many scientists in Estonian marine science and to go around with the vessel. We should have this kind of either with the other countries together or a multi-purpose. It's quite clear. But I hope it will be so. We have been talking about it already 10 years, but now it seems that there is at least a very good hope.
Okay, there is one question from
Tuli
Zoom.
Quite right. Minu taas on uks lahti.
There is one question from Zoom.
Mhm.
Are there any plans about avoiding chemical weapons?
Not by myself, but I know that our university and School of Science, this chemical department, they have been involved, and I hope I know that at least that there are some applications to study them further. And mostly those scientific groups are from Poland and Finland and Germany, but not so much from Estonia, but at least from this faculty, we have also participants who have been part of that. It's good that we don't have them in Estonian office. The places are somewhere else.
Some other questions or comments, please. Okay, if there are no questions at the moment, then I would like to thank you very much for your participation. And yes, this event also wouldn't be possible without our cooperation partners. So I would like to thank Tallinn University of Technology for welcoming us today here and for supporting us in organizing this event. And I would also like to thank our colleague from Mecklenburg-West Pomerania University Information Office, Diana Vaivodica, for cooperation and support and following us in Zoom. And finally, I would like to thank all of you for coming up here today and to be being active. And thank you for your attention and have a great weekend.